Good afternoon, ladies and gentlemen. I would like to introduce a keynote speech by one of the fathers of the Internet, Dr. Robert Bob Kahn, Chairman, CEO, and President of the Corporation for National Research and Initiatives, CNRI. Thank you.
Hello, everyone. I'm Bob Kahn, President and CEO of Corporation for National Research Initiatives in the U.S. In the early days of computer networking, the scientific community speculated about the benefits of computer-to-computer communication. Practical approaches to achieving it had not yet appeared. It was clear that reliance on dial-up telephone circuits was problematic at best, since they were slow and error-prone, not to mention inefficient and sequential in nature. Higher speed dedicated lines were about to be introduced, but the need to connect end computers directly with each other was inefficient and much too costly. Still, the notion of how computers would actually talk to each other was left to each individual's imagination. While there has been much progress in the last 5 decades, advances in artificial intelligence today provide a similar set of challenges as scientists and engineers try to imagine how these stunning new capabilities can affect us in the future. The main insight in those early days was the recognition that infrastructure was essential to the successful development of computer communications. Many of these insights are relevant today. In addition to the associated technical issues, connecting end computers directly to each other also required every computer to accommodate every other new computer when it arrived, a burdensome and unsustainable requirement. And evolving the system of communication required that any changes in the methodology would have to be implemented in every participating computer for it to continue to be an active and working participant. If all the computers were in a building or campus, other alternatives were possible, of which the Ethernet later became the most popular choice. But to minimize the cost of connecting many widely distributed computers in a network, the notion of store and forward was introduced, along with the concept of packet switching, which was viewed as a more efficient way of using communication lines by sharing them with multiple user streams. A packet was defined as a sequence of bits with a network address to which the packet was to be delivered, and it had sufficient error checking with retransmission to assure highly reliable end-to-end communications. Initially, it was assumed that each computer would perform the store-forward function using an appropriate routing algorithm until the packet finally arrived at its intended destination. But each of the computers along the way were assumed to be busy serving its users, and that might interfere with its ability to process store and forward packets in a timely way. Hence was born the notion of a separate network to implement the store and forward functions. The first such network was the ARPANET, created by ARPA in the late 1960s, although actual use of the network did not occur until a few years later. It was first publicly demonstrated in Washington, D.C. in October 1972. In addition to the architectural notion of a separate packet switch in it, it was recognized that the computers would need a way of communicating with each other, assuming packets could be reliably delivered to them. Thus was introduced the new field of host protocols, where each connected computer was viewed as a host on the network. All the early engineering work was done by motivated folks in the research community, but very quickly it became apparent that industry was better suited to undertake this need going forward. Suppliers of operating systems now started to provide the host protocols in their software releases, and hardware suppliers made available interfaces between the host computers and the network. All these developments had little to do with the applications that users cared about, however, which were largely email and file transfer initially. But it established the importance of an infrastructure to support computer communications, and more importantly, an agreed architecture on which it was based. When several additional networks was as networks were subsequently developed, there was a need to interconnect them in their computers as before, only now an inter-networking architecture was needed. Having been very familiar with and intimately involved with the work that had come before, my colleague Vint Cerf and I generated a new architecture that became known as the Internet, and we worked with the research community to bring it to reality. There were different approaches generated by others, to be sure, but eventually the value of a single architectural approach won out, and some 50 years later, while it has evolved almost continually since then, it still works in roughly the same fashion as before, only with new and improved networking gear, new and improved host protocols that embrace the internet and many new applications not really practical or envisioned before. Still, the task of using the internet still relied on the use of keyboards and screens to navigate the various computers. And while computer communications and storage technology have all evolved greatly over the past 50 years, I choose to focus instead on the underlying architecture and infrastructure that enables these remarkable technologies to interoperate. In the late 1980s, Vint and I wrote a paper subtitled The World of Knowbots, which described how smart mobile programs we thought of as knowledge robots or simply knowbots could free the users from constantly being at their keyboards and watching their displays. We envisioned these mobile programs as consisting of AI programs that could carry out a set of distributed tasks in a network environment and bring back answers to its users. If they had to visit a dozen sites along the way, that is what they would do. Alternatively, we could have limited ourselves to mobile programs that would seek only pieces of information and bring all the pieces back to the user for local processing, if that were practical. But it would have put the burden on the user's machine to do all the remaining work in the final analysis. And some of the data to be returned might have been sizable. So we thought it better to do the computation out there on the net where the relevant data resided. Thus was envisioned an infrastructure to support this distributed function, which we call the Knowbot operating environment. I still think this is a good idea, but we had to put it on the back burner at the time, as the Mars worm appeared at about the same time, and all the industrial folks we talked to were skeptical of receiving in their systems mobile programs written by unknown others. Much of that thinking survives to this day, but the circumstances have now changed. Given the aversion to processing mobile programs written by others, we decided to focus on a more static version of the Knowbot technology, which is known as the digital object architecture. You can find a description of it in ITU recommendation X.1255, which was written in the context of identity management. The key elements here are digital objects, sometimes referred to as digital entities, which have unique identifiers that are resolvable to the objects themselves. More importantly, they convey provenance information about the objects, which is particularly important when information is accessed by AI programs and some degree of attribution is needed, or for copyright purposes, when derivative works are created, which will be increasingly important over time. An important aspect of digital objects involves a general purpose protocol known as the Digital Object Interface Protocol, or DOIP, which enables one to interface directly with a digital object anywhere in the internet. Among other things, it conveys the identity of a digital object, the identity of the action to be taken on that object, and certain security information, as these are all based on the communication of identifiers. The DOIP interface should therefore remain an excellent choice almost without change as the system evolves over time. This protocol is administered by the nonprofit Dana Foundation, based in Geneva, Switzerland, and is available as open source software for anyone to use. See the dana.net site. The digital object architecture is also the basis behind the FAIR-DO efforts in Europe. When you combine the new generation of AI software with repositories supporting a DOIP interface, amazing things can happen. These new software packages with their large language models, can accept natural language inputs and generate the software to drive the DOIP interface, thus relieving the user of the need to do so themselves. A standard way to deal with digital objects is needed, so that multiple varieties of AI software can interface with them. That way, we can continue to encourage new and better versions of AI software to be developed without worrying about having all the data stored in digital object repositories to adapt to each new version. I encourage you all to explore this interesting new infrastructural approach and see the wonder that architectural standards applied this way can bring. And then, when we have a firsthand appreciation of the value of this important step, perhaps we can explore together how to turn it into a real world of knowbot programs milling about the internet on behalf of users now freed from being continually at their keyboards and watching their screens. To achieve this will require some additional architectural changes and the participation of the industry in widely disseminating the corresponding infrastructure. Let me close with a few comments about the IGF itself. It's important that the internet continue to evolve along the lines described above, and as others will propose over time. When the idea of the IGF was first proposed at the second phase of the WSIS in Tunis in 2005, it was unclear how it would fare over time as a forum for discussion. Many thought it might only last a few years. But what is surprising is that it not only has lasted almost 20 years, but that it has seen an enthusiasm expressed by its attendees in its growth over the years and in the number of local IG instances that have developed all over the world. There are very few regular forums on a global basis where civil society can make its views known and have them discussed. I congratulate the MAG for arranging a very up-to-date agenda for this meeting, but it will be important to continue this trend in the future and to encourage new faces to participate in its deliberations going forward. It is especially important, I believe, to clarify three things for the attendees now and in the future. One, what topics should the IBM be discussing? Two, how should discussion of government policy fit in, if at all? And three, how much of the discussion should be about technology itself? I believe the IGF has served a very useful purpose over the years and would encourage the UN to renew its charter. Thank you, and I wish you all a very successful conference.
Thank you, Robert Kahn. We're all grateful to your pioneering spirit. For the rest of you, we'll see you at the Taking Stock session. Thank you.